Previously, we looked at wind loads. Now let's examine seismic impact. Seismicity is also a horizontal load, but its nature is fundamentally different. During an earthquake, vibrations don't start outside the building, but right beneath it in the ground. The building's foundation starts moving horizontally with the ground, but the building's mass tends to stay put due to inertia. This discrepancy is what generates the seismic force. It's directed horizontally and acts upon the entire structure. Unlike wind, seismic load depends primarily on the mass of the building. The heavier the building, the greater the seismic force. That's the main difference from wind. Seismic force equals the product of the building's mass and the ground's seismic acceleration. This acceleration depends on the seismicity of the area. It's expressed in points on the MSK64 scale. In Kazakhstan, most cities are located in zones of 7, 8, and 9 points. The higher the point rating, the greater the ground acceleration, and the stronger the seismic load. Seismic force isn't just applied at the base, but is distributed across the building's entire height. Each floor carries its share of the load, proportional to the floor's mass and height. The higher the floor, the greater its contribution to the total seismic load. It's similar to wind. The load also increases with height, but for a different reason. With wind, the airflow speed increases. With seismicity, the vibration amplitude grows. The load from each floor is transferred through the floor slab to the vertical structures. The main load-bearing elements are shear walls, monolithic walls, and structural cores. They act as vertical cantilevers fixed into the foundation. It's important that the shear walls are arranged symmetrically in the plan. If the center of rigidity doesn't align with the center of mass, the building starts to twist. This torsional effect significantly increases the load on the outermost elements. Besides the area's point rating, the soil type also affects the magnitude of the seismic load. Weak soils, like water-saturated sands, amplify vibrations and increase the load. Rocky soils, on the other hand, dampen vibrations and reduce the seismic impact. The building's natural frequency of vibration is also important. If it matches the ground's vibration frequency, resonance occurs. During resonance, the vibration amplitude spikes and the structure faces loads many times greater. Engineers check the building for displacement and the strength of load-bearing structures. If displacements exceed allowable limits, they increase shear wall rigidity or add new ones. Seismic isolation is also used, special bearings between the foundation and building that absorb ground vibrations. In high-rise buildings, dampers are installed. They dampen the structure's vibrations. All these solutions are regulated by building codes. In the next video, we'll look at how seismic load calculations are performed using formulas.